Swayam Prabha. Digital India. Educated India.
So, in the last class we have discussed about that first question, what is chemical engineering, but I do not know how many of you have the real definitions of chemical engineering. I have one definition, this is given by AICHE, I do not know whether you heard of this or not. What is that AICHE? Huh? American Institute of Chemical Engineers. We remember everything about America. Okay, so American Institute of Chemical Engineers definition, I will just read, please write, because let it be there in the books. I do not know whether you really spend time to understand this, but let it be there. I think when time is required, I think when this is required, so you can try to use this definition. Yeah, the official definition of AICHE is sufficiently broad to include all aspects of the profession. Now you can write within inverted commas. Chemical engineering is the application of the principles of physical sciences, together with the principles of economics and human relations to fields that pertain directly that pertain directly to processes and process equipment in which matter is treated to effect to effect a change in state, energy content or composition. Okay, that is the one. I think inverted commas closed. Yeah. So, Gani, can you read this louder so that everyone, I think you have to also give the meaning. Okay. Okay.
Physical sciences together with the principles of economics and human relations to fields that pertain directly to processes and process equipments in which matter is treated to affect a change in state, energy content or composition.
Yeah, I think what is that you said, the first one, chemical engineering is the application of the principles of physical sciences. Principles missing? Yeah, I think some people would have missed it. Yeah, chemical engineering is the, what is the meaning of that? Can you just read it and then just try to understand? What is the meaning of that? What is the meaning of that? Louder. I think you can interact with me, there is no problem, you should not be afraid that you are not able to tell and all that, we are all learning. So, that is why absolutely there is no fear for making mistakes, you should not be afraid of making mistakes, you should happily make the mistakes as many as possible, but only thing is you should not repeat them. Okay. Tomorrow also you cannot do the same mistake. Yeah.
Physical science means all the chemistry, all the physical sciences.
All sciences, yeah.
That using the knowledge of that sciences and about the economic viability of for the economics of profit.
Yeah, economic principles. Yeah, that means whether process is economic or not. Yeah, then.
And also how it affect the interaction of the process with the in general environment of people.
Environment has not come here in this one. Okay, yeah, but don't create your own definition. Just understand this definition. Yeah, then we will create our own definitions later. Yeah.
The relation with the human there.
Yeah, the human relations also are very, very important. That's what this is physical sciences, that means maths, physics, chemistry. These all, of course, chemical engineering is based on that mainly. Now we have biochemistry also. This is one of the oldest definitions. So, pertain to the that pertain directly to processes and process equipment in which matter is treated to affect a change in state, energy content or composition. This last sentence also, state, energy content or composition. So, that means during the reaction, if everything is in gas phase, so then you have to condense that and then you can make it as a liquid or liquid to solid. Okay, that is the state thing. And also energy content, that means it may be at very high temperatures, you have to cool it to room temperature, because you cannot store everything only at high temperatures. So, the changes in composition or energy content or state, that covers everything. That means in which equipment you are changing the state,
Condenser
but that is only physical process. But in the reactor also you are changing the state, because sometimes during the reaction itself precipitation occurs, and then that is itself is the product. Okay. So, this covers few equipment, and also energy content. Energy content mostly, of course, even in the reactors again you add heat, remove heat and all that, means you are trying to change the energy content of that, and also composition in which equipment, distillation columns, absorption columns and all that. So, that means this also talks everything, almost all the equipment. Okay. So, all this equipment, finally equipment design, even though most of the young faculty members nowadays they get very bored about, you also the moment you become faculty member also you hate equipment design. Okay. Why? Because there are not much mathematics involved. There are only some rules that to design, for example, condensers or heat exchangers or distillation columns. You have some principles. So, just follow them and then design. So, what is the thrill there, people say. But ultimately all the theory what you have developed finally will go to this part, and if you neglect the end part and if you are very happy only with the theory part, then who will use your theory? Okay. So, that is the reason why all this entire thing is very important. We need theory to understand, right. Like for example, distillation columns always we see it is vertical and also number of plates and all that, but now people started thinking about very small size of the equipment for distillation, and they use centrifugal force. When it is moving, the liquid will be just simply spread on the thin sheets at a very high speed. So, then in a thin when you have very thin sheets of liquid, then evaporation is much easier, right. So, the low volatiles will easily come out and high volatiles will stay there. So, then you are separating very fast, and you have 20 meters 30 meters distillation columns. Now, you have become only 6 feet 7 feet, that means 2 meters 3 meters. So, that is because of the new theory. You are now able to think that at molecular level what is happening and how do you use that information to create very thin film, and we know that when you have a very thin film of molecules, it is very easy for the molecules to come out because resistance is simply less, right. So, that is the theory, and using that theory you are able to develop this equipment. So, finally, the ultimate aim is only the equipment design. Otherwise, where do you conduct these reactions, where do you conduct separation processes or crystallization, all these processes where do you conduct unless you have this kind of equipment. And also nanotechnology, we very fashionable word to use many times, but at the end what do you do with that nanotechnology? You should still design a reactor or some other equipment for our processes. So, that is why do not simply get carried away with these beautiful words unless you understand those words and unless you use those words properly for the final design. See, ultimate aim of our profession is to produce chemicals, that is all. So, that is the second definition I just want to tell. This is the official definition. The second definition is that a simple definition is a chemical engineer carries out large scale reactions developed in the laboratory by the chemist. Yeah. So, the chemist will definitely try to find out whether reaction is feasible or not, but minute scale micrograms. But with micrograms, I think nowadays if you get headache after this class and go to hospital, and then they will give you disprin tablet or some other analgin or many tablets are there. Okay. So, if you look at them, then there will be amount also given 500 mg. So, they may not produce even this 500 mg for one person sufficient. Okay. So, that is what actually happened in penicillin production. They could not produce on large scale. One patient actually in UK, he has got some infection that made him I think 1 week or so or 4 days 5 days all right, and because they could not continue, they did not have sufficient amount of antibiotics they produced in the laboratory, and afterwards he died. That is, I mean, it is bad thing to say like that, but his operation successful, patient died. Because as far as antibiotics are concerned, that was successful, they know how to produce now on a small scale, but unfortunately this patient could not get sufficient amount of antibiotics, so he died. right. So, that is why our business is as chemical engineers to produce chemicals on very large scale. Generally the starting point is a chemist. He would have produced and told that yeah, this product is there, so it may be useful for this and all that. Good. Yeah. Then again I think this some of you may be knowing a jocular definition of chemical engineering. You know, anyone knows about this jocular definition of chemical engineering? No. Yeah, I will tell you, a chemical engineer is one, another definition. This is a jocular definition, you can write jocular definition. A chemical engineer is one who talks engineering in the presence of chemists. A chemical engineer is one who talks engineering in the presence of chemists, comma, chemistry in the presence of engineers, chemistry in the presence of engineers, comma, and politics in the presence of both. That is the definition. Okay. What do you understand this? That means we do not know sufficient amount of chemistry, we do not know sufficient amount of engineering, and when both are there, I think our ignorance should not come out. We divert the topic to politics, because politics anyone can talk, because everyone has an opinion in politics, right. Yeah, but there is a beautiful meaning behind this definition. Even though it is jocular definition, it is not really jocular, it is very serious definition, because behind many jokes there is serious information. Okay. That means this is the only engineering which is based on science, okay, from the beginning, right. That means what? Unless you understand basic chemistry, you cannot carry out further your processes. That is what is the meaning, right. So, a chemist who is a scientist, who has sufficient knowledge in that science, right. So, he should have sufficient information how to produce this chemical. It is not by trial and error. Theoretically also he should be able to find out that okay, this is feasible because of this reason, this reason, this reason. So, afterwards you cannot produce large amounts because of engineering coming there. For example, I told you mixing is a kind of engineering principle, heat exchange is a kind of engineering principle, right, on large scale. How do you do that? So, that is why engineering will come into picture. So, engineering knowledge is necessary. In fact, in the beginning it is applied chemists, not even pure chemists, applied chemists and mechanical engineers are the people who are producing chemicals. I am talking about 1800s, 1700s. Okay. So, the definition of chemical engineer at that time was applied chemist plus mechanical engineer equal to chemical engineer, right. And then they thought that okay, we need separate profession where we need some information on the science side. Of course, physics automatically comes whenever you have heat transfer, fluid flow and all that, right. And without maths you cannot quantify. The greatness of maths is anything you want to say in a number, maths automatically come, and unfortunately or fortunately you have to tell a number. So, if someone asks okay, tell me the design of this particular reactor, you say okay, use 1 meter cubed volume. 1 meter cubed is a number, and how do you calculate that 1 meter cubed and all that? Again you have to use some equation. So, mathematics you can never neglect at all. It is a part of all the processes. Every day also I think mathematics you use. I think when you have 20 rupees and go for Tiffany's and coffee may be 25 rupees. So, then you may come back over 5 rupees less subtraction. Okay. Nowadays everything is costly. No, I do not know what is, how much is the, what is the cost, Rahul? 6 rupees, huh? 7. 7 they are cribbing a lot, because this is subsidy given to the students. So, that is why they are cribbing a lot. So, but anyway, anything, everything, there may be a time now coming, with the inflation that is going on, even 100 rupees you do not get one coffee also. Okay. Anyway, coffee is bad for health, do not drink. Okay. So, that way you can escape. For that 100 rupees you can buy a fruit, a small fruit, and then eat whatever fruit that comes. That is much better. Okay. So, this is another definition, and the latest definition that is given by Den. I do not know whether you heard of him, Martin Den, DENN. He has written a book recently, maybe 1 year back or 2 years back, Chemical Engineering and Introduction. Chemical Engineering and Introduction. Okay, that is the name of the book. DENN, double N. With one N he is not happy. So, DENN, Martin Den. Okay. Martin Den. Okay. Good. he wrote that book Chemical Engineering and Introduction. In our library also 1 or 2 books may be there, and of course he started at a high funda level and all that, but anyway one of the definitions he has given, this is the maybe current definition. Please write that chemical engineering is the field of applied science that employs physical, chemical, and biochemical rate processes for the betterment of humanity. That is the latest definition. And if you go to UK chemical engineering site, you will have a different definition. If you go to India, it will be a different definition. If you go to Japan, chemical engineering society and all that, so they may have slight differentiation, but the ultimate aim is to produce chemicals and biochemicals. That is why chemical engineering and biochemical engineering no way different. Here you need chemistry background, chemistry information for the reaction, whether it is taking place or on a catalyst or all that theory. And in biochemistry, biochemical engineering, you need information on biological processes, right. So if you have sufficient knowledge there, and you know that there is a reaction that can be that can be conducted, then that information will automatically come into the reactor design. So that is why chemical engineering and biochemical engineering or biotechnology, if you are talking about production of chemicals in the industrial level, at the industrial level. Okay. So biochemical engineering or biotechnology or chemical engineering all are same. In fact, chemical engineering is so wide. For example, environmental engineering. Many civil engineers start environment engineering, but the real environmental engineering is only with chemical engineering. The reason is most of the pollution is from the chemical industries. Okay. And civil engineers have come into picture because traditionally they were the people who are treating sewage, and that sewage is mainly from human waste and kitchen waste and all that, that is all. So they logically extended their field, saying that okay, we will also talk about these pollutions, but it is chemical engineers who create pollution, and also it is our business to control pollution. Now zero pollution, you should have the processes, you should have heard green chemistry, green engineering and all that. So idea there is that you do not have to produce any waste product at all. So it must be at the end everything should be useful. Okay, those are the new processes which we are not yet started teaching in the chemical engineering. Few universities abroad I think they started, but we do not have green chemical engineering or green processes. We do not have no. Yeah. So and also sustainability engineering. Sustainability engineering environment always is coupled. Okay. So that is why new definitions will be coming depending on the situation, current situation on this planet. And this definition you see, it is again very simple and straightforward. Applied science, chemical engineering is the field of applied science that employs physical, chemical and biochemical rate processes, rate of reaction, right. So that rate of reaction you should use in the reactor design expression, so that you will produce. And if you are able to produce using, I told you, dream reactor. What is dream reactor? Yeah, directly reactor reactants to products at room temperature, 100% conversion, and that means there is no separation processes, no byproducts. So separation processes are not required, because at room temperature in the beginning you do not have to heat the reactants, everything at room temperature. So beautiful. I think we are going to try to design that kind of processes. Dream. That is what is really sustainable. You do not need any energy. Try to produce ammonia at room temperature and room pressure, you will be given Nobel Prize. Not 1, 10. Yeah, I think Haber got only 1, because still his temperatures are very high, okay, and pressures are very high. At least reduce the pressure and conduct the ammonia reaction, ammonia synthesis reaction at ambient pressure, you will get one Nobel Prize. Temperature also if you reduce, 2, okay, and catalyst if you remove, 3, because now you need catalyst, right. What catalyst they used? Iron of course mixed with slight yeah, all other small metals are there, but mainly it is iron, okay, and he found it. In fact, I was lucky to see his room where he has worked on this process, in University of Karlsruhe in Germany. I also worked there for some time. So, at that time I saw his room, and his reactor has been now brought after I think maybe I do not know how many years, maybe 15-20 years of operation, actual reactor which he and other person Bosch, Haber and Bosch, that is why Haber Bosch process we say. Bosch was is not directly chemical engineer, but he declared himself as a chemical engineer, because he was dealing with all chemical engineering processes in BASF. BASF is a company, you should have heard, no? Yeah, BASF has a nice expansion in Germany, German language. So, he after he produced that in lab scale reactor also is there. If you promise me that you will read the papers which I send, I can send wonderful information, but otherwise I do not want to create e-pollution. E-pollution, that means I send the paper to you, you just click and save, and then you never open that again. Okay, that is pollution, no? On your computer you are not using that, it is waste, that is a waste product only, right. So, that is why if you promise, all of you, if you promise me, I will read, and then only I will send. I think in fact I have the picture of his original reactor, lab scale as well as industrial scale. Now you appreciate most of these things we also teach in process calculations, whatever I am telling you now, right. But at that time you never really able to enjoy what we are trying to say, but at this point of time you enjoy. That is the reason why I repeat. Many people may be thinking that he does not know anything except this, so that is why he is repeating. People may be thinking, okay, but you know, because I enjoy, because at this point of time you enjoy more all these things. Otherwise, you know, whatever you learnt in school, you may not enjoy in school. You learn only, you enjoy only when you come to UG or PG. How beautiful you know we have learnt in the school. So that is why always there is a time lag. That is why I repeat all these things in my course, so that at least some of you may catch this and then try to enjoy. Okay? And there are some minds which have already been switched off, they come here, sit, laugh and then go, but I think nothing will enter. Like black holes, at least people say radiation will come out. Okay? You know, radiation can be measured from black holes. Black hole means, you know, you cannot see anything. So, I think the human mind is, if you switch off the brain, human mind is much worse than black hole. You do not know anything what is happening there. Okay, and perfect insulators are human brains. Yeah, if you are able to take and then put it, nothing will enter, nothing will come out. That is why at least, you know, some matter in black hole will radiate. Okay, so that is also not possible. So if you already have, you know, normally you will have around 20-15% already switched off brains, they come, sit down and then go. And those are the people who really spoil, you know, the juniors who are coming. Unfortunately, if those people are exposed to these 10-15%, they give all fully wrong information, complete total virus, you cannot clean it with anything. Okay? No antivirus dot is possible for that. So unfortunately, many people will go and ask them only, they won't ask a good student. Good student means you will definitely tell, no, no, this is good, this is bad, and clearly you can believe him. But unfortunately, for them it is everything bad except staying in the hostel, okay, and seeing movies and all that, right. So that is why this is very unfortunate if you ask them. So that is why I am not talking about the 10%. I do not know right now who is the 10%, but statistics show that the 10-15% already exist, okay, but not able to pinpoint right now, but you know yourself. You definitely know whether you are enjoying it or whether you want to learn or simply come because your guide told or someone else told that you have to take this. So it is a punishment. So 40 hours, 50 hours punishment. So that is what probably you are doing it, that is all. But anyway, if you do not have a choice, try to relax and enjoy, okay, because all MTech people you do not have a choice. It is compulsory for you, okay, and I think PhD also compulsory. PhD also I think compulsory because for their comprehensive or something, okay. So that is why those who do not have choice, try to learn something. If you have choice, put a hole through the ceiling and then go out, okay, like Superman or something like that, you know, put a hole and go, okay, good. So this is what is the complete answer for the first question, what is chemical engineering, okay. Now the second question is, what do we do as chemical engineers, okay. The reason is most of the chemical engineers are going for IT jobs. So they think that only going to IT job is chemical engineering. That is what is the job of the chemical engineer. So if you ask them to write what do chemical engineering do, go to Infosys, open the computer and then do whatever they give exercise. That is what people may think. Okay? But what are the things what a chemical engineer can do? I will just list out here and then discuss one by one very quickly. Okay? The second question is, what does a chemical engineer able to squeeze there. Yeah. The first one is research. Process development. Process design. And evaluation. Process design, okay. Plant design. Okay, I think I will write all these things in one: plant design, construction, and operation. Then we have product supervision. Plant technical service. Technical service. And then product sales. So, those are the things. Able to see last benches? Able to see, no size? Okay, good. So, these are the ones. The first one is research. Okay. Chemical engineering automatically associated with research, whereas this research component, if I take mechanical engineering example, it is not there. So, if you are designing a boiler or if they are designing a automobile, okay, generally the principles are known, but if I want to design a new chemical, I do not know anything. And how many chemicals you can list out? In inorganic chemistry, how many? In organic chemistry, how many? How many chemicals? Thousands of chemicals. And the beauty with chemical engineering is every process has a flow chart. How do you develop that flow chart? Without a flow chart, did you any time see a particular production of a chemical? Never. So, how that particular flow chart was developed? And now, of course, if I know how do you produce sulfuric acid, I do not have to do research, even though it is possible. Okay? And nothing is saturated in chemical engineering. Those people who say that, oh, chemical engineering saturated means, it is not chemical engineering saturated, it is his brain saturated. Okay? Because he is not able to see anything different. So, this is saturated, he is happy, and then like going to IT. IT, what is there? They give some instructions and then you follow on the computer and lifelong you do there. And if you are, and they will not allow you, they will give you more money, but they will also give you more work and always sitting. So, that is why after 3-4 years you will have back pain, okay, stomach will be coming this much, okay, because I think where is the physical activity? There is no physical activity, there is no mental activity also, because already everything is known. You just only enter, that is all. I mean, if you are developing a new software, excellent. If you are developing or using these computers, like that Jurassic Park movie you have seen, that is entire thing is computer controlled. Those big structures, maybe height maybe 50 feet, 60 feet high, those 1 or 2 models what they have shown. So, if you are doing that, excellent, or even if you are making at least beautiful cartoons, very good, no problem, because cartoon movies and all that, lot of computer work is there. So, at least you are using brain, because if you are producing the same cartoon in two movies, no one will see the second movie. That is why I feel that in movies only there is tremendous of innovation, tremendous amount of innovation. Really, I appreciate them. How many dresses they change in one song, I say, and you have to think so much, right? No one will go to that movie. First information will go, it is same thing as other movie close. Okay, so that's all, and they are spending thousands of and fights. Oh my God, sometimes I think if man is not sufficient, 2 cars will come and fight and 2 aeroplanes will come and fight. Oh my God, anything. Tremendous innovation is only in movies. So if you have that kind of innovation, no problem, but in chemical engineering that innovation is there. Okay, why? Because every chemical is new to me. If it is already existing, like sulfuric acid, I told you, no, what is the first step? Sulfur is burned to sulfur dioxide, then sulfur dioxide is converted to sulfur trioxide, and we know the catalyst. And the beauty is the first one is non catalytic reaction, it is sulfur plus oxygen giving you SO2. The second reaction SO2 to SO3 is SO2 plus of O2 giving you SO3 in the presence of vanadium pentoxide. How do I know? The first one does not have any catalyst, the second one has catalyst. How do I know that? Okay, and this is not only the final process, but can you produce also sulfuric acid, this SO2 to SO3 without catalyst? That is why it is beautiful engineering, chemical engineering. Unfortunately, many people mistake that with chemistry, right? So like that, any process you take, ammonia I told you, bring down the temperature. Now I think people are working on that. Now I think the temperature has come down to around 130 or so. Earlier it was 250. How much was the temperature? I don't remember exact value for ammonia. 550, and pressure 350. Okay, yeah, okay, 200 bar, and then this is 550. You bring down that one to 100 or 200 degrees centigrade. How much energy is saved? And bring down the pressure from 200 250 atmosphere to even 10 atmospheres. Your design will be so simple now. Otherwise, you are operating an atom bomb at 250 atmospheres. That is why the original reactor which I saw there in Germany, I think the nut and bolt itself is this thick and then this long, solid iron, and the flanges thickness I think is 6 inches or 8 inches. Yeah, I think I have that photo also I have taken. I will show you sometime. I will bring and then show you that one. Okay, so that is the kind of thing. All that materials of construction, all that will become very less the moment you come to, of course room temperature is too ambitious, but at least 100 degrees centigrade. So that is why everywhere research in chemical engineering, provided you don't know the process. That means someone would have already done that. Sulfuric acid also, it took a long time for the development. In fact, because of sulfuric acid only chemical engineering started. I don't know how many of you really know this. Because of purely the sulfuric acid, chemical engineering started because of that only. What is the connection? Connection is industrial revolution. In industrial revolution, the first thing many people started doing that at that time was the steam engine, and the next thing is all the people were trying to produce textiles as many as possible. That is why Manchester, this Coimbatore also is called Manchester of India. Okay, because the conditions are correct there to make the textiles and all that. Okay, and for textiles you have to put dye. So to produce dyes you need sulfuric acid, and sulfuric acid at that time was only produced in glass reactors. How much big glass reactor you can make? You cannot make bigger. You cannot make more than 50 liters or 100 liters glass, right? So that is why they want to produce more and more. That is why they have gone to that first process, lead chamber process, because of the corrosion. Then of course afterwards contact process, this process, that process, many processes have come, and during that time people realized that my God, there is heat transfer coming, there is mass transfer coming, there is fluid flow coming, and all these things are not there in one engineering. With reactions, fluid flow mechanical engineers do, even civil engineers do, hydraulics they call, right? And mass transfer to some extent the mechanical engineers do in combustion, because when they are burning coal, without oxygen they can't burn coal. Oxygen has to be supplied to the coal surface. So then only the reaction takes place. So that is the reason why there is some amount of some knowledge is required, how much oxygen is being transferred continuously to the surface of coal. So all those things also, heat transfer they are experts anyway, they are better than us heat transfer, because most of the time we don't worry about radiation, but they will worry about radiation and all that, right? So they have more knowledge than us. but still reactions means they will run away. Okay. Even now coal combustion they do, but mainly coal combustion is controlled by mass transfer, oxygen supply. The kinetics is but of course there also they have increased the combustion science and technology. They are doing also a lot of work, but all that can be done easily by chemical engineers. So that is why chemical engineering started, and that is why research is the one where in every process you need this. What kind of research we do? We do research as basic research. I will just write here basic. We can also write exploratory, and we have process research. Process research, CH, yeah. Okay. So I do not know whether you know the meanings of all this. This is for research. Basic research we call. We also say that we are doing fundamental research. If I take one example, probably it will be easy for you to remember this, right. Let us talk about some catalytic reaction. Okay. For example, ammonia production itself, right. So recently in 2008 I think, that is recent only, one person got Nobel Prize in Germany for telling the mechanism of this hydrogen, ammonia synthesis, this hydrogen and nitrogen, how they combine on the surface, what is happening on the surface. He is not worried about what kind of reactor he has to use. He took the catalyst and then he wanted to study on the surface how the molecules are going and sitting, what is the orientation that is for proper reaction, and what is happening during the reaction. All that he has designed the equipment and then shown that actually what is happening during reaction, and he also extended that study for CO, carbon monoxide to carbon dioxide, a few more reactions. For that he got the Nobel Prize. The greatest of him is that his name is Ertl, ERTL. We also wanted to bring him here, but I think he is not able to, it seems, travel, maybe health is not good, right. So that is why he has shown what is happening, particularly for CO2 he excited a lot. It seems on the surface also there are some kind of waves generated during the reaction. If you go to his website Ertl, ERTL, okay, Nobel laureate Ertl, he has got a website where all this information is very nicely given, the mechanism is given. So that is what we are talking here in the basic research, that much information is required for us, otherwise it is blind macroscopic research. Okay, that is process research. What you just take a solid surface as catalyst, some solid, trial and error, change the solid, whether the reaction is taking place, no, this is no reaction, bring another solid, different metals. You go to periodic table and then take metals. If one is not producing any chemical, any product, then mix two metals. Maybe I think you are telling iron and cobalt. Again percentage, what is the composition? You can vary from 0 to 100. 0 did not work, you know that. Okay. So 100 also would have not worked at the other side. So now in between combinations. So that is what is trial and error research, where not much theory, it is not basic, that is exploratory. That means you are only trying to find out what is feasible, what is not feasible. Okay. And in the basic research you just try to find out some new theories based on your observations. That is why I told you, unless you have the experimental verification, no one will get Nobel Prize for only just producing theory. That is why theory producers some of you also may be very much interested in theory, because you do not have to do the experiments. Experiments means doing with hand, that means your hands may get dirtied and most of you may not like it. Okay. And I tell you, there is only pleasure in doing the experiments, because what you are doing you are seeing, you have the control, whereas in theory, change the boundary condition, you will get another equation, another solution, right, in the differential equations. Most of the time in theory you start with only differential equations. So in theory what do? You imagine the process, take a small volume if there is a continuous change in that volume, and then you write the elemental balance on that, Bird, Stewart, Lightfoot approach. That book is famous only for that, elemental volumes. and then extend that from entry to exit, that is boundary conditions, and then solve this equation. And when you are solving that equation, you may find out what is the concentration change or the velocity change with the distance, okay, or with the geometry inside the the particular equipment, or temperature, concentration and velocity, only these three: mass, momentum and heat, right. That is all. And from that you will now to try to find out the moment temperature is given, concentration is given, velocity is given, you can find out what is called flux. That means you know how much has been transferred from one place to other place and all that. You can find out, no, the moment we give an equation for concentration, can you find out flux? You cannot. I have concentration versus length as an equation. Flux you cannot find. What is Fick's law definition? You know only definition, but you don't know how to use it. Na flux equal to what? dCA by? What is that dCA by dz?
Concentration gradient.
Yeah, if I give you concentration versus length, but to find out that differentiation and then evaluate wherever you want, right? Yeah. So then why do you say that you don't know how to find out? Because application we don't know. We have theory, but we don't know how to apply that. In fact, that is one of the favorite problems in GATE, and I was GATE chairman. That was in 2000. Okay, yeah. So that is a very nice problem, very simple problem, because as all of you know that you mug up beautifully fixed first law and second law, and you don't know when a problem is given how to use this information to find out flux, right. So that is all. And in the basic research, what you find out is that kind of new theories. For example, in mass transfer you have various theories, film theory, right, and also Higgins penetration theory, and what is the third one? Surface renewal theory. All these theories are coming from basic research. In fact, these theories are not that basic as I told you for this Nobel Prize on the surface, because still in this theory, penetration theory, we never talk about molecules. We talk about only a group of molecules, a bulk of molecules moving from one place to the other place. We know only in film theory, across the film all the resistance is there and molecules are moving from this side to that side, but still you are not worried about how individual molecules are moving. So that is why in basic research what you try to do is development of new theories, right. So with the understanding of that catalyst, what kind of catalyst to use, what kind of every catalyst has that holes, defects and all that. So what kind of defects are required, all that you can produce if you understand that theory. That is what is basic research. And we have the exploratory research where trial and error most of the time, right. Catalyst is very good example. One catalyst you try, you don't know. Normally we have one thumb rule that okay, this periodic table may give you some of the periodic table elements will behave as catalysts. So you take only those and then try to find out whether this is what combination or a single metal is useful for catalyst. All that trial and error, that is exploratory. At the end what you record is what is the for that particular reaction, what are possible catalysts, what are not possible catalysts, so that others they need not again repeat. And in process research, this is normally many people won't do except the laboratories, regional research laboratories or NCL Pune. So they take the reaction, it is not only one reaction they do it, and you would have heard of laboratory scale, then pilot plant scale and then finally commercial scale. Laboratory scale also there are 2-3 varieties, simple lab or bench scale. Bench scale where chemical engineers come, lab scale is only still chemists, right. So you conduct some experiments in the laboratory scale, you are not confident that straight away this can be scaled up to industrial scale. So then what you have to do, you have to do some experiments in between, and for that some experiment you now decide whether you have to go for bench scale or pilot plant scale or the ultimate scale. Ultimate scale, direct scale up is not possible for many reactions. That is what we do in the process research. At the end of the process research, what you will have roughly, okay, on this 1 kg scale, I have all the information starting from raw material to product. That means, if you want a condenser, you have to use a small glass column. If you have a reactor, use a small glass beaker. If it is a continuous one, and input and output together. So, all that information you would like to get that in the process design, process research, right. Laboratory scale only, you limit only till laboratory scale. The moment you come to process development, that is where you come to now either bench scale or large scale or pilot plant scale. Large scale I am talking compared to laboratory scale. So, in the process development, what we do is using pilot plant and then trying to get as much as data possible, so that you will not have much problem in the actual scale. What data you get in process development? For example, you have a bubble column. Single phase is not that difficult, but two phase heterogeneous systems are difficult in scale up. Why? Because I may take a laboratory and then beautifully bubble, all bubbles are very nice, same size and all that. The moment I go to very large, reactors are as big as these rooms also. So, here how do I produce those kind of bubbles with uniform size? That is what is a big scale up problem. And in the laboratory, small bubbles, more surface area per unit volume, but here in the large scale you have large bubbles, surface area will decrease. So, in the laboratory you may get 90% conversion, in the actual scale you may get only 30% conversion. Simply interfacial area is not reproducible at that scale. How do you do that to reproduce? Whether you go for multi-stage, whether you put many dispersers, whether you put stirrers where you break the bubbles, or whether you put in between perforated plates where big bubble will go and touch the perforated plate and it cannot pass through. So, that is why it has to break itself and then again go to the next two plates, all that. So, all that information is required here in the process development, so that you can go for big scale.